Okay, so now what we're going to do is we're going to run through an example of pathfinding in code format. Now I do want to make a couple notes. First of all, this is a very, very simplistic example. It's meant just to demonstrate finding the path. What you do with that path is completely up to you. In some games you may have something chasing something else, or you may just have something highlighted. It all depends. The examples I was showing you before, like if we run this program right now, we have our example here, and if I hit the space key, we get the path showing up. Doesn't do a whole lot. Of course, there are more complicated examples as well. Let me show you one that I have. This one's in Java, but it's still the same thing. Just run this over here. Here we have a more complicated example, and let me just turn a few things on. I'm going to turn on the grid, which I'm going to do with the G key. Oops, the G key, so I have the grid so I can see the layout of the world. Next thing I do is I'm going to turn on path lines. So in this example, we have a target down here, and each one of these little squares is a chaser. Each one is trying to reach to the goal. Now I can actually move this player around, and by moving this player around, the chasers actually have to recalculate their path every step of the way. So 60 times a second, they're actually recalculating because I can move while the program is running. So I'm going to hit go and then pause it for a second. And first thing I'm going to do is I'm going to turn off that tile sharing. Let me turn that off. Let me resume it. Now you'll notice each one is maintaining their own path. So I'm over here. Now if I start to move, some of them are going to catch me. And when they do catch me, they're going to basically turn off. And I can see their stats right now if I hit the T key, where every one of them is on right now, and it's showing me their current path. Each one has their path coordinates. Okay, let me turn that off. So I'm going to get this going, and I'm going to move around using the WASD key, see if I can get away. Leave me alone. You notice that they have different terrain types that they have to deal with, and they move slower over certain terrain types. You see them slow down over the sand. They don't slow down too much over the water. But in any case, this is a much more complicated version where you have dynamic things happening. You got the player moving, you got the enemies moving, you have different paths showing up. Sometimes the paths can intersect, sometimes they don't have to intersect. It all depends. And of course there's different terrain types and everything like that. Alright, so how am I going to show you this? Well, I'm going to show you this by going through the whole process, the setup and everything like that. And then we're going to focus on the actual pathfinding logic. But I do have to mention and remind you of a few caveats. First and foremost, you need to understand how a 2D array works. So go back over to the class website and check out the 2D array stuff. Second thing you're going to need to know, you're going to need at least a basic understanding of how classes and objects work, because we are going to be using them. Now if we look at our program here, you're also going to need to know how a list works as well. Now if I look at our program here, we have this world that's built up of a grid. Now the grid is just overlaid over top. There's not really a grid there. It's me manufacturing a grid. And I'm going to say that everything works on this grid system. Now it's me as a programmer deciding that. How big the grid is, how small it is completely up to me. If you're playing a three-dimensional game, something like Skyrim or something like that, it still works on the exact same principle. It's still going to create this grid. It's not going to be squares. It's probably going to be triangles or something along those lines to map out the entire world. And that's how pathfinding works in those games. They don't just walk in a straight line. Otherwise, they'd walk straight through hills and stuff. Their grid actually maps it to the terrain and over top of hills and mountains and everything like that. And when they talk about which part of the terrain is walkable, what they really look at is like the incline of a given area. So for example, a sheer wall cliff is going to have such a high H value, such a high G value that it's going to be impossible to walk on. Whereas something like a slope, a gentle slope, is going to have a very low G value. In fact, it might even have a less than standard G value because it's gravity is playing in here. Anyways, just to go through a little bit of terminology, I'm going to interchangeably use the word tile and node. Tile means one of these squares, and for our purposes, when we're doing our pathfinding, each square is one node in the path. And we usually reference these things in two ways: grid coordinates, so row and column, and ordered sequence coordinates. So for example, this first blue part of the water here, I can see that that's on row 0, column 0, 1, 2, 3, 4, 5, 6. So it's located at 0, 6. What actual element number of our entire map is it? Well, it's exactly 6. So if our entire map is numbered 0 all the way down to 239, then it's going to be numbered from left to right, top to bottom. So this square down here would actually be 0 to 19, then 20, 21, 22, 23, 24, 25, 26. This would have the ID of 26. So we reference our nodes in both these ways, row and column as well as ID number. And this just simplifies some processes for us later on. Alright, so if you're comfortable with this stuff, continue on. If not, pause the video, go check out the other material or refresh that other material before you move on, because it's just going to confuse you, and it's already a confusing topic as it is. So go get that under your belt before you venture into this, please. Okay, let's get started. So the first thing we're going to do is we're going to set up different data. Now, in this example, I use a little bit of keyboard logic to maintain the space key, to figure out when the user hits the space key. I also have two simple images in here. One, a 1x1 blank pixel, and I just stretch that pixel out to create lines. Very simple. It's just like stretching a rectangle. I just stretch it out and create a line out of it. Tile image, that's just a very simple blank square. If I look at this, it's just a white square with a black border. That's all it is. And if I apply color to it, that color will only apply to the white, and the black will be left alone. All right, so I can basically color my tiles anytime, any size, or any color I want. The next thing I do is I go over this tile size. So I've decided I'm going to use the default XNA resolution of 800 by 480, and I tried to find a common factor that would be reasonable sized. So I found that if I have a tile size of 40 pixels, both width and height, then I actually get a nice even spread for our screen size, in which case we're actually going to get 12 rows and 20 columns. Simple. The next thing I did is I've designated a whole bunch of constants to refer to each one of my tile types. This allows me to get rid of those magic numbers, and I'm going to definitely want to do that for this setup. So what I'm going to do is I'm going to use these things for a number of purposes. First of all, to get rid of magic numbers. Second thing I'm going to use it for is it allows me to easily use this number inside of an array index so I can reference certain information. So for example, if I want to know the color, I have this array of tile colors of a road, I would say tile colors square bracket road, and that would give me the value color.light gray. That way I don't have to have a different variable for each one of the tile colors. I just have an array of tile colors and use that number as my reference, as my index. So the second thing I do, or I guess not second, but the next thing I do is I've actually created a 2D array of integers to represent our map. Now I have three different maps here. You saw them in the previous video, the basic example, more complex C example, backwards C example, and then the final multi-terrain type example. Now I just have two of them commented out for cleanliness purposes, but in any case, so I have this set up and it's just a 2D array. So I have 12 rows and 20 columns. And I've just specified what each type of tile each element is. So it just goes through blank, 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 water, 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 water. And I just go through and I specify those. Now remember, each one of these is just an integer. It's just a constant integer up here. And I use this so I can easily look at this and say, well, I know what my map looks like just by looking at this, not a whole bunch of 3s, 2s, and 1s. That doesn't mean anything to me. That's the worst form of magic number possible. So that's all of our graphical data. The next thing we have is we actually have our pathfinding data. And there's not actually much pathfinding data at all. That's it, just this little bit here. What kind of things are we storing? Well, one of the things we're going to have to do is we're always going to be checking that open and close lists, and we're going to say is an element that I'm looking for in one of those lists. And it's either going to find it, and it's going to tell us what index it's found at, or it's not going to be able to find it. In which case, we're going to have it return a -1. But again, to get rid of magic numbers, we're going to use this not found value. So similar to storing the colors in an array and just referencing the the number constant as our index, I'm going to do the exact same thing with the cost to actually walk on each one of those tiles. So my tile costs. So if I want to know how expensive a road is, I'd say tile cost square bracket road. And that would tell me that it's 0.5 times the standard cost. 0.5 of the horizontal vertical cost, or 0.5 of the diagonal cost. So again, this allows me to simplify and makes my code cleaner. The next stuff I have is just keeping track of all the nodes and the lists and everything. So I have a 2D array of nodes, which is our node representation of this integer array. So what we're going to do is we're going to basically go through this integer array for every single one of these. We're going to create a node object, which is going to maintain all the information of a given node. I'll go back to figure out what that actually means in a second. And we're going to have a 2D array of this. So what is a node? Well, a node is basically just a data class, and it maintains all the important information about every single node. Now, every node maintains its own information. So every node has its own F, G, and H cost. Every node has its own parent. Every node has its own row, column ID, and tile type. Similarly speaking, every single node is going to maintain its own list of adjacent nodes, nodes that touch it. And then they're also going to maintain their own graphical data, where their rectangle is located and what color they're going to be drawn at. So whenever I create a new node, I have to specify where it is, what type of tile it is, and what color it is, as well as the size of the overall map. And I use that to create the actual location of the to calculate the actual ID. Remember the left to right, top to bottom ID that I was talking about before. Alright, and then at some point we're going to have to calculate the adjacencies. Now remember, the adjacencies is just, it's going to look at all of the touching nodes around that given node, and it's going to say, alright, you're a valid adjacent node if two things are true. If you're on the map and you're a walkable terrain type. So for example, a blank terrain type, water, mud, whatever, those are all walkable. What are not walkable are things like walls, maybe pits of death or spikes or something like that, whatever your game has. So that is going to be called later on. So going back to our actual main class here, we're also going to track which one is our start node and which one is our end node. And this is for the purposes of deciding when we're done and how to actually get our path. This here is our list of all the path nodes. So this is going to be useful when we're actually reconstructing our path after we've finished doing our path finding. And then of course we have our two buckets, our open list and our closed list. As long as there's elements in the open list, we can continue. If the closed list has the final space, the final node, we're done. We found a path. That's it. So what's our setup? Not much setup really. Let's take a quick look at it. In load content, we're going to load our images because we need to. We're going to specify our map size in terms of number of rows and number of columns. We're also going to set up how big our node array is. And then for this piece right here, it just does a very simple process. It goes through our integer 2D array of tile types, and it just says, all right, for every one of these, I'm going to create a node version of that tile type. So it's going to say, well, specify its location based on the row and column of our nested loop here. And then it's going to say, well, what tile type is it? And what color is it? That's it. And then down here, we just detect which one of these is a start and the end space. So which one's a chaser and which one is the target. And that tells us which one is our start and which one is our end node. And we need that for later purposes, as I mentioned before. Then below here, we're going to go through every single node in the node 2D array and we're going to call the set adjacency. So it's going to detect all of its own individual adjacent nodes. And then finally, we have our set H cost. Now this is an interesting thing. Now we're doing set H costs here in load content, which means it only happens once per program. This can only occur like this if you are creating a program where the target doesn't move. If the target doesn't move, then you're good. However, if the target moves, you're going to actually have to call set H costs every single update, because you need to recalculate it because the H is now different. So that's our setup. In our update, not much here. All I'm doing is saying when you hit a space key, toggle the path on and off. So if I don't already have a path, find the path. If I do have a path, clear the path. So it just toggles it on and off, as we saw here. Toggle it on, off, on, off, on, off. Whenever I toggle it on, it's actually recalculating the whole path. Okay. Drawing, not much drawing code. We keep it very simple here. We're drawing our terrain, which is all of the tiles. We're drawing our grid, which is just the grid over top that overlays the whole thing, and then our path. Now, of course, the path isn't going to draw anything unless we actually have a path. So logically, what does this look like? Well, for our draw terrain, it's just going to go through, and depending on what type of tile it is, as long as it's not blank, it draws that tile type at the current location based on row and column. Draw path does a very similar thing. It's going to go through the list of path nodes, and it's going to draw each one of those nodes at its corresponding location with a color of yellow. I'm going to force it to yellow so I know which ones are actually path nodes. And then the grid is a very simple thing. As I said before, we have a 1 by 1 pixel that I basically stretch out horizontally for horizontal lines and vertically for vertical lines. So there's not much to that. That just draws lines, horizontal line and draw vertical line. And I use these over here. I just do 2 for loops. I do a for loop that draws all my horizontal lines, then I draw a for loop that draws all my vertical lines. That's it. So that's all the graphical stuff. That's all the setup. We haven't even talked about the pathfinding yet. The pathfinding is actually a lot less code. There's not much to it. You can see that we're already 2/3 of the way through the program. So what do we do in the find path? Well, we follow, we follow the 8-step process here. We start by setting the G to 0. Going over here, set G to 0. Whenever we change G or H, we have to recalculate F because it's changed. Once we've set the starting G to 0, we're going to add the start to our open list. So we're just following the list. So that's number 2. Now we get into our loop, and it says keep looping until we either find a path, which means the target was added to the closed list, or the path is impossible because there's no more elements, no more nodes in the open list to check. So we go down inside of our loop. So inside of our loop, it's going to follow a very simple process. First thing it's going to do, it says calculate the smallest f out of all of the nodes inside the open list. So it's going to loop through all the elements, and it's going to say which one is the smallest one. Once we know the smallest one, we're going to store that smallest one and call it current node. We're going to remove it from the open list, and we're going to add it to the closed list. So every time that we add an element to the closed list, add a node to the closed list, we got to check to see whether that node was the ending node. If it was, we're done. We don't need to do any more work. So we break out. However, most times that's not going to be the case. So we actually have to continue. So once we've added our current node to the closed list, we now need to go through all of the adjacent nodes of that current node. And we're going to say, well, which of these adjacent nodes are likely candidates. Okay? So for every one of the adjacent nodes, we're going to follow the 4-step process. 5A, ignore it if it's already in the closed list. It's already been checked out, so we can ignore it. B and C kind of work together. B and C says if it's not in the open list, then set its parent to the current node, recalculate its G, its H, and its F, and then add it to the open list. C says, hey, you're already in the open list. Let's check if the current node, which is the new potential parent, is a better fit. And it will be a better fit if that node has a smaller G value as a result of using the new parent. If it does, then we reset its parent, we reset its G and F cost, and we continue. It's already in the open list, so we don't need to add it. And then finally, we'll come back to this last part, this 5D, in just 1 second. All right, so A, 5A, down here, right here. Check to see if it's not in the closed list and it's a walkable type. So we don't do any work on this adjacent node if it's not valid. We know it's not valid if I can't walk on it or if it's already in the closed list. So if it is walkable and it's not in the closed list, then we continue on and we go to 5B and C. With both of these cases, we're going to need to know what the new potential G value is. So we're going to calculate that immediately. So I call this subprogram called get G cost, and it says what is the cost coming from the parent to the new node, to the adjacent node. Once I've done that, now I'm going to do the actual work of B and C. Well, is it already in the open list? If it's not in the open list, great, it's a new node that's not there. Let's set its parent equal to current node, where it came from, and then we're going to recalculate, we're going to set the G value, which we already calculated up here, and then we have to recalculate F because we changed the G value, and now we're going to add it to the open list. So now there's more elements in the open list. So even if some elements fail, we still have more to look through. And then finally, if it is already in the open list, so down here, if it is already in the open list, now we're going to compare it. Is the new G better than the old G? If the new G is better, that means that the new parent is better. So we're going to reset the parent equal to current node. We're going to set the G equal to the newly calculated G, and which means every time we calculate G or H, we have to recalculate F. Okay. So that's going to keep going and keep going and keep going. But at some point, we're going to keep going through all those elements in the open list, and eventually, we may run into the situation where there's none left. If there's no more elements in the open list, break out. There's no path. Can't do anything about it. Sorry. So then we come down into here. If we're outside of the while loop, we've either found a path or we haven't found a path. We know we've found a path if it's not, or sorry, if the target is in the closed list. So if it is, then the system is very simple. We start with the end node and we look at its parent, and then we look at its parent, then we look at its parent, then we look at its parent, and we keep doing this until we get to the start node, which has no parent. And every time we look at one of these nodes, we add it to our list, our path list. And it always goes to the front of the path list. And that will ensure that the earliest node is at the front, which means we're going to go from start to end, as opposed to end to start. Once you have that path, return it. That's the work of the entire path finding. So there are some support subprograms that I've created below to help simplify that process. So for example, get H cost, that does the Manhattan heuristic. It says how many times do I need to move to the side, how many times do I need to move vertically. Multiply that by the H cost and the multiply each one of those by the HV cost and add it together, and you have the Manhattan heuristic result. That's our H. The set H basically just goes through every single node in the 2D array, recalculates its H, and then recalculates its F as a result of calculating H, of course. And then down below here we have our get G cost. This does a bit of the magic. It says, all right, if the current node is the parent and the adjacent node is the comparison node, okay, what direction did we have to travel to go to get from the parent node to the comparison node, the adjacent node? If it was a horizontal or vertical, we're going to go into this first setup. If it was diagonal, we're going to go into the second setup. In which case, we're going to take the cost of getting to the parent from the start, and then the cost of moving horizontal or vertical, and we're going to multiply that cost by the type of tile cost. Now, if you don't have different terrain types, you don't need this last bit. You could just have the parent G plus the HV cost. Similarly speaking down here for the diagonal. And then last but not least, a very simple for loop that goes through whatever list I want to check and says, does the node that I'm checking for exist in that list? I can use this subprogram for both my open list and my closed list, which I will need both for. And if it finds it, it returns the index it was found at. If it doesn't find it, it returns -1 or not found. So that's it. That is pathfinding in C# form. It's pathfinding in general form, and hopefully you got what you need to. Hopefully you can construct this and work with this and actually produce something effective. Good luck.